So I hope my screen is visible to every one of you. Can you please confirm that? Okay, thank you. Let me see if the recording has started. Yeah, the recording is going on. Good evening, everyone. Today is the second week of analog circuits, and myself again Chaitanya Kumar from IIT Madras, and I will be taking your tutorial for the second week. Again, one request from every one of you that I want the session to be interactive. I will give time for you guys to solve the problems that I have for you today. And if you solve them, you practice them. Naturally, your concepts will become more stronger because these kind of subjects have a lot of numericals in it, and more numericals you solve, the better it is for your overall concept command over the concept. So having said that, let's start with the first problem. So uh, you guys are familiar with control sources, right? Guys, you can unmute yourself and answer the questions that I ask, and it will be better for me as well because I will know that I am teaching a live class. So you guys know about control. So this is a circuit which involves a control source, and I hope you guys are familiar with control sources. Can you guys confirm what all control sources are there that exist? Anyone? Anyone who will like to answer this? How many types of control sources exist?
Voltage sources, voltage
Uh,
control current sources,
Voltage control voltage
similarly,
sources, voltage control current
similarly,
sources, and
current control voltage sources,
current control voltage sources, and
current control current sources.
current control current sources. So in this circuit, can you identify which control source is present? So what is the controlling parameter? So this is the control source, right? What is the controlling parameter?
Current,
No, the controlling parameter. What is controlling the current in this?
voltage,
Yeah, which voltage?
Vx,
Vx, right? So it's a voltage controlled source, and what is the output? The output is a
current source,
current. Out of these four, which one it is?
CCVS,
VCVS.
CCVS,
Volt. No, no, it's voltage controlled. So the controlling terminal comes first. A controlling parameter comes first. It's voltage controlled. So it's VC and current source. So this is a VCCS.
okay sir,
Okay. Okay. So please help me solve this. So basically, in this question, where in this network you have some resistors and a voltage controlled current source, and you are asked to find out the gain from the input to the output of this particular circuit. So can you guys help me solve this question? So please help me write the nodal equation of at the node Vx, what we will have at Vx. So can you guys help me write the current equation? So there will be three currents flowing out of Vx, right? Please help me. So what you will have? You will have Ia, Ib, and Ic, correct? So can you help? And what is the KCL at this node? Ia plus KCL. I will use some different pen for the solution. So KCL at node at Vx, you have Ia plus Ib plus Ic is equal to 0, correct? Now, what is Ia? Can you guys help me write the Ia, Ib, Ic?
IA is equal to V1 by R1.
Are you sure? What is Ia? What is the direction in which Ia is flowing? It is flowing inside the node or outside the node? Out of the node.
Out of the node.
Out of the node. So, in this direction, whatever current is flowing, what you will write it as? This is Ia. So, what it will be? It will be basically the potential difference across this resistor divided by the value of this resistance, right?
Yes.
Yeah. So, what is the potential difference across this resistor?
Vx minus Vi divided by R1
Okay, correct. So, Vx minus Vi divided by R1 is Ia. What is Ib?
plus Vx by R3
Vx
plus
by R3 plus
Vx minus V naught divided by R2.
Vx minus V naught divided by R2. Correct. This is equal to 0. So, what is the other node on which we can apply KCL? So, which other node I can apply KCL on? So, see, this node has a voltage source over it, right? So, the current over here is unknown, right? So, applying KCL on this node doesn't make sense. So, on which node you can apply KCL? The other node is V naught. And how many unknowns are there? Vi is known, right? Vi is equal to, so Vi is the input voltage. And for that itself, you need to find out what output you will have. So Vi is known. There are two unknown that are Vx and V naught. Okay. So at Vx, you have written KCL. Other place where you can write KCL is V naught. Okay. So you will have two equations, two unknown. You can solve the solve this thing. So help me write. How many currents are flowing out of the node V naught?
3
Three. KCL at V naught. Can you help me write KCL at V naught?
IC is equal to GM Vx um,
Uh, okay.
plus
Let's this node for this node. Let's have a separate set of currents. Let's call this IA hat. Let's call this IB hat, and let's call this IC hat. Okay. So what we will have? IA hat plus IB hat plus IC hat is equal to 0. Now, what is IA hat?
sir, why we are choosing the IA direction in opposite? We can
What we are trying to do is you can do that, but yeah, just for systematic approach so that chances of error reduces. I am just choosing that from all the nodes when I'm writing the KCL, I am choosing the direction of the currents from those nodes to be in a single direction, so that so that all those currents can amount to 0.
okay.
Later you can manipulate it, but yeah, if you do that, you will. So there, you can do it anyways. But yeah, I find this thing more uniform. So,
V naught minus Vx divided by R2
we have V naught minus Vx divided by R2 plus
plus GM Vx
GMVX
plus V naught by RL.
V naught by RL is equal to 0. This is equation 1. This is equation 2. So the above one. This is equation 1. So equation 1 can be rewritten as coefficients of Vx and V naught as. So we will have Vx 1 by R1 plus 1 by R3 plus 1 by R2 minus V naught by R2 is equal to Vi by R1. Correct? So one can be written like this. So let's call this equation 3. 2 in terms of Vx and V naught can be written as. So what will be the coefficient of Vx? What we will have over
R2,
here?
R2 plus R3 plus R1 divided by R1 R2. R3.
Okay. No, no, no. I am trying to resolve equation 2 in terms
Okay.
of in terms of coefficients of Vx and V naught. Can you help me with that?
GM minus 1 divided by
Gm
R. Minus 1 divided by
minus
R2
1 divided by R2 is
plus
your plus
V naught. If you take
V naught.
common, 1 divided by R2 plus 1 divided by R. It's
Thank
equal
you.
to 0.
So this is equation 4. So what we are interested in? We are interested in V naught, right? So what we can do is, so what will happen is, if we just divide equation 3 by coefficient of Vx, let's call that CVx, and subtract it from equation 4 divided by, so CVx3 divided by coefficient of Vx in equation 4, we will get something in terms of Vi and V naught. And from there, we can find out V naught. So let's try doing that. So what is CVx3? So CVx3 is this term. This is CVx3 and this is CVx4. So what is CVx3? We have R3 R2 plus R2 R1 plus R1 R3 divided by R1 R2 R3. Correct? And what is CVx4? GM R2 minus 1 by R2. Is this clear? Is this clear? Okay. So we will just do that, perform this operation. So what we get is minus V naught by R2 times R1 R2 R3 divided by R3 R2 plus R2 R1 plus R1 R3 is equal to Vi by R1 times the same thing, right? R1 R2 R3. So then here we will have Vx, right? By R1 R2 plus R2 R3. Guys, you guys can also try to solve parallelly with me, and if you get the answer quickly, you can just raise your hand and tell me the answer also. Okay, plus R3 R1. So this is how it will look, right? Is the third equation written correctly? Okay, so the other equation, how we will write? We have to subtract this equation from Vx plus V naught 1 by R2 plus 1 by RL times R2 by GM R2 minus 1. This is equal to 0. This is equal to 0. Okay. So if you subtract the two equations, what you get over here is minus V. In the first equation, what you can do, you can remove this R2 by R2 and over here R1 by R1. Is this correct? So what you get is minus V naught R1 R3 divided by, so let's for convenience, let's call this particular term as D, so that our equations become a little more little less cluttered. So we have R1 R3 by D minus, so this can be again written as by taking the LCM. LCM is R2 RL. So we will have R2 plus RL, and R2 and R2 can be cancelled. So we have RL times GM R2 minus 1 is equal to VI R2 R3 times D. Is this clear, guys? Here will be a plus over here. Is this equation clear? I hope this equation is clear. So till this point, any doubt or any problem? This is just plain algebra, guys. So I hope you guys can follow this, right?
Yes, sir.
Yeah. So again, so what is V naught by Vi from this? We have, if we take out R1, R3 common from this, so what we will have is R2 by R3 times D times R1, R3 divided by 1 by D plus R2 plus RL upon GM R2 minus 1 times uh, R1, R3. Okay, and if D we take inside, so R3 and R3 will be removed from here, and if we take D inside, so we have minus R2 by R1 divided by 1 plus D times R2 plus R3 divided by GM R2 minus 1 times R1 by times R1 R3. So this is how the equation looks. It looks complicated, right? So what is the what was the second part of the question? The second part of the question asks what happens if GM tends to infinity. So looking at this equation, can you tell me, so what happens if GM tends to infinity? What is the value of V naught by Vi?
Minus R2 divided by R.
Minus R2 divided by R1, correct? So do you think it just came by fluke, as in why did it come? Minus R2 by R1. Let's redraw the circuit again. Okay. So what happens if R2 is infinity? Okay. What happens if GM tends to infinity? Let's try to figure out from the circuit itself, right? So what happens if this Vx is so let's say if Vx is some finite value, what will happen? If let's say Vx has some value that is not equal to zero, what will happen to the current if Gm tends to infinity? So let's say Vx is greater than zero. Okay. If Vx is greater than zero, what will happen to the current, this current, if Gm tends to infinity? This Gm is tending to infinity. Come on, guys.
It is a dependent source, sir. GM is nothing but the current divided by that voltage. If so, the voltage must be zero in order to make that GM equal to infinity. No, sir.
No, no. GM is basically the value of the dependent current source. GM is the fixed value of this particular element. You can't make GM as zero. So GM comes by design. So for example, this value of RL, it doesn't depend on what input you are giving. Correct. So there will be some V naught. The current flowing through this will be V naught by RL. So depending on so if RL goes to, let's say, infinity, the current from the current flowing into RL will become zero. So that's how you look at it. Okay, so this is not basically saying that whatever the current is, that I will divide it by Vx, and if Vx is zero, then it will become Gm tend to infinity. Gm is something that is given to you. So if, let's say, the given GM is very large or tending to infinity, in that case, what will happen? What will be the current that will be flowing through this current controlled voltage controlled current source?
Will be maximum, sir. I don't know.
It will be infinite, right?
Okay, sir.
Okay, infinite, or let's say if there is some power supply limit to this voltage controlled current source, it will just saturate to that. Correct.
Okay, sir.
Yeah.
Yeah.
So if, let's say, very huge current is flowing through this, okay, extreme amount of current is flowing from this direction. So what will it do? So let's say there will be infinite there will be current division, and current division of an infinite current will also be almost infinite only, right? So if infinite current is flowing through this, if infinite current is flowing through this resistor, and let's say this Vi is some positive value, what actually Vx will become? So Vi minus infinity times R1. Where will Vx tend to?
It tend to zero.
Actually, it will try to go to minus infinity, right? Because this is some finite value. This our resistor has some finite value. So Vx minus infinity times R1 will try to go to minus infinity, right?
Okay.
Yeah. Now, now anything doesn't instantaneously moves to some value. It takes some time, right? So if let's say some Vx was some greater than zero quantity and infinite current started flowing through this, so Vx will start going towards minus infinity. Now, as the Vx is going towards minus infinity, the current that this guy is taking out, since the current depends on the Vx, as the Vx is going through minus infinity, it will try to cross the zero axis, right? So if it try to cross the zero axis, this current starts reducing and reducing, and the moment it comes to zero, this current also becomes this basically becomes a zero by zero kind of term, so it becomes a finite value. Does the am I making sense?
So can you come again?
Okay, so basically, so what I am saying is, let's say Vx is greater than zero. Okay, that means to say GMVx will tend to infinity, right? If GM tends to infinity. Till here it is correct?
Okay.
Yeah. Now what will happen if GM tends to infinity? Let's say this current was I1. So this current will basically divide from between these two guys, right? And then there will be some division between uh, of the current between I1 and whatever is flowing from here. Let's say I3. So all these will be some factor of so I1, I3, or maybe I2. All these will be some factor of GM times Vx, right?
Yeah.
Yeah. So this I1 will also start tending to infinity, right? If like the so some I1 will be some alpha times GM Vx. So if GM is tending to infinity, I1 will also tend to infinity, right?
Yeah.
Okay. Just a minute. Yeah. So if that is the case, then Vx that is equal to Vi minus R1 times I1 will tend to minus infinity, right? Is this clear? Because I1 is tending to infinity, then Vi minus R1 times I1 has to tend to minus infinity, right?
So, whether I'm correct, you can correct it, sir. GM values initially it is infinity. Since the
Yeah.
Vx value goes to minus infinity, it the current is going to zero. That is what you're
Correct.
explaining.
As Vx, so basically what I'm trying to say is this is contradictory, right? So I initially assumed that Vx will be greater than zero. At the end, I am getting Vx as minus infinity, a huge negative value. So my initial assumption was incorrect, right? You can look at this way. Is this clear now? So Vx can't be greater than zero. Clear up to here?
Okay, sir.
Yeah. Now, if okay, Vx can't be equal to zero, then what is the other condition that you can have? Vx, let's say, can be less than zero. Let's assume that so this is basically contradictory. Correct. So other assumption we can make is assumption two. I will redraw the circuit over here or copy the circuit over here. Vx is less than 0. So Vx greater than 0 is not possible. We saw it just now. Let's say Vx is less than 0. In that case, Gm Vx will tend to
Minus infinity.
Gm Vx will tend to minus infinity. And then Vx, so then I1 will tend to minus infinity only, right? Because I1 is some factor of Gm times Vx. Correct? Then Vx, that is equal to Vi minus Vi minus I1 times R1 will tend to,
Sir, is that minus into minus plus infinity? It doesn't work like that.
of course, there a huge negative quantity into negative into minus 1 will be a huge positive quantity, right?
Yeah.
Yeah, so it will tend to plus infinity. This is again contradictory, right? We assumed Vx to be less than 0, but we are seeing that Vx is equal to plus infinity. So this is also contradictory. So Vx can't be less than 0, Vx can't be greater than 0. Then what can be the value of Vx?
Is
Zero,
that
sir.
yeah, okay, 0.
0, right? So assumption 3, Vx is equal to 0. Okay. Now, if Vx is equal to 0, then can you comment on what will happen? So, what will be Gm times Vx?
It's
Zero.
0.
It won't be 0. It will be infinity times 0. This is a limit, right? You have learned the concept of limits in your 12th class, right? So, infinity times 0 is not it. So, you will have to determine it based on whatever function you have. The factors of the function, one factor of the function is becoming infinity, other factor of the function is becoming 0, then you will have to apply limits to find its actual value. You are aware of this concept, right?
Yeah, can you just briefly explain that what is? Just a
So,
formula.
okay, so let's say, so basically, let's say sine x divided by x, limit tending to 0. Okay, so you can see it as limit x tending to 0. If you need to find this, what you will do? So you can just see it as sine x times 1 by x, right? So what will 1 by x tend to? If x is tending to 0, what will 1 by x tend to?
Infinity.
Infinity. And what will sine x tend to?
0.
0. Correct? So it's again the 0 into infinity. Now how will you find that? How will you find its actual value? So you will do some assumption. If x is tending to 0, sin x will tend to sin
0.
x is if so I think in trigonometry you have learned this. If x is very small, sin x is equal to
It's we take 0.
no. Let's say x is a very small quantity. It's not exactly 0. It's, let's say, very small quantity. Then what will be the value of sin x approximately?
I don't know, sir. You can say that.
Okay, this through trigonometry, if x is tending to 0, sin x is approximately equal to x. You can see it in the graph as well.
Okay, okay.
So basically, it goes like this. The graph of sin x goes like this, right?
Yeah.
Yeah. So So if the graph of sin x goes like this, if you zoom in around this where x is tending to 0, it will almost be like a straight line, y is equal to x kind of line.
Okay.
Okay, so basically sin x will be approximately equal to x. So if x is tending to 0, that means x is a very small quantity and sin x can be written only as x. In that case, what we will have is, it will so this can approximately be written as x by x, which is equal to 1. Okay,
Yeah.
so this is basically the concepts of limit. So when you have two terms, so 0 into infinity or 0 by 0 or infinity by infinity, something like that, if you have, in that case you need to apply concept of limits in order to find what will be the limit to which that function will approach to. Is this clear?
Yeah, yeah. Go on.
Okay, so to find out what happens when Vx equal to 0, since it's 0 times infinity, we will have to see where the values of currents and voltage of the circuit approach to. So this is how we will find out what will be the current that will be flowing through this current source and other values. Okay, so let's copy this circuit with the assumption Vx equal to 0. We are assuming Vx equal to 0 and Gm is tending to infinity. Now, if Vx is equal to 0, what will be the current flowing through R3?
It's infinity.
No, it's 0. What is the potential drop across R3?
I think it's Vx. It's zero, sir.
0. Potential drop is 0 across a resistor. What will be the current flowing through that resistor?
Is it zero?
It's 0, right? What is the current through a resistor? Potential drop divided by the resistance, right?
Yeah, yeah.
Yeah, so it will be 0, correct? So if the potential drop across this resistor is 0, so what will be the current flowing through R1?
VI by R1.
VI by R1, right? Okay. Now if VI by R1 is flowing and the current through I3 is equal to 0, so what will be the current flowing through R2?
Same thing, VI by R1.
VI by R1. So if Vx is equal to 0, current flowing through R2 is VI by R1. So what is V 0?
Minus R2 divided by R1 into V.
Minus R2 divided by R1 into VI, right? So this is what you got over here, correct? V 0 by Vi was minus R2 divided by R1 into Vi. Is this clear? So that means to say our assumption of Vx equal to 0 has been verified from the methodological approach as well. So if Gm was tending to infinity, V 0 by Vi was tending to minus R2 by R1. And with the assumption of Vx equal to 0 in that case, we can also find the same thing as V 0 is equal to minus R2 by R1 times Vi. Is this clear?
Yeah.
Okay. So if having said this, so if this is clear, so can so does this approach of assuming Vx equal to 0, finding current through R1 and passing the same current through R2 and hence finding the output voltage, do you think you have seen a familiar circuit where you apply all these concepts? So, in the analog circuits only, from in the course so far, you might have seen some circuit where you apply similar concepts in order to find output voltage. One node is assumed to be
DAC digital to analog converter, sir.
not exactly. Think a little more. In okay, Harsha said amplifier. What kind of amplifier? So, what kind of basic two amplifiers you have studied till now?
It's inverting.
Inverting and non-inverting, two amplifiers you have studied, right? So where do you apply this concept, where Vx is equal to 0, Vi is equal to
That virtual ground concept, sir.
yeah, virtual ground concept. You apply it in negative inverting amplifier, right? And in inverting amplifier also, the gain is of this form only, right?
Yeah.
Yeah. So what we are doing over here is we are trying to implement inverting amplifier only. How does an inverting amplifier look? So if this was R1, if this gain was tending to infinity, op amp's gain was tending to infinity, this Vx will be equal to 0, and we have R2 over here. If we put any, so V out will be minus R2 by R1, correct? This is how you calculate this, right?
Yeah.
Yeah, and what happens if there is some RL over here? Does this impact the output voltage?
No, sir.
No. And the same thing is happening over here, right? RL is not impacting the output voltage. Okay. What happens if there is some R3 over here? So this is Vx equal to 0, right? What happens if there is some R3 over here?
Summing
There is
amplifier.
no use, sir.
This is Vi. And no. If this is connected to ground, will there any current flow through R3?
No, no.
No. And the same thing is happening over here, right?
Yes.
Okay. So basically, what I have done right now, I have just drawn the internal of this op amp. Can you see this?
Yes, sir.
Okay. Now, you might think that so what you have studied as an as op amp as it is a like till now what you have studied. Op amp is a what kind of control source?
Voltage, controlled voltage source.
Voltage controlled current source. But here, what I did, I made an op amp through.
Voltage control voltage source.
No. This is not a voltage controlled voltage source. What is this? Yeah, what kind of control source is this?
Current control voltage source.
Voltage controlled current source, right? It is controlled by a voltage Vx and current is being controlled. So we till now we saw that if a voltage controlled voltage source is very high gain, connected in negative feedback will give you virtual ground. Now here a voltage controlled current source with very high gain is also giving you virtual ground. Can you see this? Okay. So the concept is here it's clear that, oh sorry, in this circuit, let's call this circuit 1. In circuit 1, it's clear that there is a negative feedback, right? Because through this R2, the negative terminal of the op amp is being hit, and this loop is being formed. It is a negative feedback. It is clear, right?
Yes, sir. This one is a voltage control voltage source.
Yeah, here it is voltage control voltage source. Now,
Uh,
can
this,
you guys see a negative feedback over here?
yes,
So,
sir.
the concept that I mentioned over here, that let's say if the Vx was trying to be greater than zero, then what the circuit will do, it will pump such a huge current that Vx can't go above zero, because it will try to bring Vx to minus infinity. And in this process, if let's say Vx was some greater than zero, to go to minus infinity, it will cross zero line. And the moment it crosses zero line, the circuit will start sourcing finite current, and it will become settle over there. Correct. So if in whichever direction we are assuming Vx to be, our circuit is trying to push the Vx in the opposite direction. The same thing happened in the assumption 2. If the Vx was assumed less than 0, the circuit, basically this GM, tried to pull up the voltage to go to positive infinity. And as it goes from some negative voltage to positive infinity, it will hit the zero voltage and become settle over there. So what this circuit is trying to do, if Vx goes, let's say, in positive direction or in negative direction, this circuit is trying to bring, do something in order to bring the voltage in the opposite direction. You can see this, right? Is this concept clear?
Yes, sir.
Yeah. So if in a circuit, the circuit is performing in such a way that that the input terminal, if let's say goes to some direction, the circuit is trying to bring the input to zero. Okay, it is trying to work in opposite direction and bring the input to zero. In that case, you will say that the circuit is in negative feedback. Is this clear?
So come again, sir.
So, in wherever you see that, so if you see a circuit like this, where there is a controlled source whose gain is going to infinity, and there is some controlling terminal. In this case, a controlling parameter is Vx. If you see the circuit like this, and it is asked that what happens if the gain of this circuit, in this case GM, goes to infinity. You will make these assumptions only, right? If you try, so let's say if Vx was less than 0, and you figure out that, okay, if you assume Vx less than 0, the Vx will actually try to go in the opposite direction to plus infinity. Or if you assume Vx greater than 0, the Vx will try to go in the opposite direction to minus infinity. In that case, you will say that the circuit is in negative feedback, and the controlling terminal, which is Vx in this case, will be equal to 0. And with
Yes,
this,
sir. Oh,
approximation, you will find out the gain from input to output. So any controlled source, either it is VCVS, VCCS, CCCS, or CCVS, any controlled source which has the gain tending to infinity, and if you can figure out that the circuit is in negative feedback, the controlling terminal will be equal to 0. Did my statement was my statement understood to you guys?
yes, sir. Yes, sir.
Can you repeat my statement in your words?
So suppose if the gain of the this type of circuit is going to infinity, the controlling part, that is Vx, should be must be zero.
Okay, and
So it
so
is the negative feedback.
yeah, if the circuit is in negative feedback and gain is going to infinity, the controlling part will be equal to zero. Okay. Now with the same thing, can you find out what is the gain from input to output in this case? Again, A is going to infinity.
Minus R2 divided by R1.
Minus R2 how can you say that this circuit is in negative feedback? What happens if Vx tries to go greater than zero?
Because A goes.
Okay, so let's say again, assume Vx is greater than zero. What will be A times Vx? What will be output voltage? V naught. What will be V naught? So this is a voltage controlled voltage source, right? If you have a voltage controlled voltage source, what will be your output voltage? V naught. V naught is equal to
A divided by 1 plus A.
no. You have A times Vx, right? So V naught is equal to
8 times VI, sir.
A times Vx.
Okay.
Okay, V naught is A times Vx or minus A times Vx?
Minus 8 times VX.
Minus A times Vx, right? Okay. So what will be minus A times Vx if A is infinity?
What is minus infinity, sir?
Minus infinity, right?
Uh,
Now, if V naught is, it will be minus infinity, right? Because minus A times Vx, A is tending to infinity, V naught will tend to minus infinity. Now, V naught, if V naught tends to minus infinity, the Vx will be some resistor divider between R2 and R1 and R3, right? Of V naught, correct? So Vx will be some. So what you can write Vx as R2. It will be fraction of some alpha times Vn plus some beta times V naught, right? So there will be you can use superposition in this particular network. If you use superposition in this particular network, what will happen? So you can first assume Vi to be 0 and V naught to be non-zero. So this node will be R1 parallel R3 divided by R2 plus R1 parallel R3, the resistor divider. Same way, if V naught is assumed to be 0 and Vi is non-zero, in this case, it will be some coefficient times Vi. So Vx can be written like this. Is this clear?
Yeah.
Yeah. So if Vx can be written like this and V naught is going to minus infinity and Vi we are giving, right? Let's say it's 1 volt. So what will Vx go to?
Minus infinity.
Minus infinity, right? Now you assumed Vx to be greater than 0 and you are getting Vx as minus infinity. So this assumption is wrong. Same way, you can prove that if Vx is less than 0, your V naught will be equal to plus infinity. Your Vx will be tending to plus infinity. So in that case also, your assumption will be wrong. Your assumption will only be correct if you assume Vx equal to 0.
Yeah, sir.
Okay. So again, what happened? There was a control source that is present in negative feedback. How do you test negative feedback? You assume the controlling terminal to be either greater than 0 and or less than 0. If due to that the voltage comes out to be in the opposite direction, the parameter comes out to be in opposite direction, that means to say the negative feedback is there. So the circuit is in negative feedback. The gain is infinity. So the controlling terminal will become 0. So Vx will become 0. If Vx becomes 0, so after that, basically current will be Vi by R1. Here no current will be flowing. And this current will flow through R2. So output will be minus R2 by R1. Correct? Okay. So, so we saw that a voltage controlled current source can be used as an op amp. A voltage controlled voltage source can also be used as an op amp. Let's try to see if, so now what is this?
Current control voltage source.
Current controlled voltage source. Let's try to see if this can be used as an op amp or not. Okay. So what happens? Again, you will see whether the circuit is in negative feedback or not. So R is tending to infinity. Okay. So again, I will assume. So this time, what is the controlling parameter?
Ix.
IX.
Ix, right? So again, I will assume Ix to be greater than 0. What will be V naught?
Minus uh, minus R into IX.
Minus R times Ix. Correct?
Is
So
it
Now,
is it plus Rx, sir?
uh, sorry.
Okay, okay. It's minus Rx, no?
Okay, let's not do this. Let's do whatever Ix is going inside this. Let's assume that. Okay, let's remove that short connection. Okay, so minus R times so if Ix is greater than 0, the voltage V naught will be minus R times Vx, minus R times Ix, because this is opposite direction voltage source, right?
Yeah, yeah.
Okay, so if it is minus R times Ix, so let's say some Vx is there over here. What will be Vx? Again, Vx will be alpha times Vi plus some beta times V naught. Now, if Ix is greater than 0 and R is tending to infinity, what will happen to V naught? V naught will go to
minus infinity. So
minus
Vx also
infinity.
goes to minus infinity.
Vx will go to minus infinity. Now, if Vx is going to minus infinity,
It is
uh,
contract.
so if Vx is going to minus infinity, the current in this direction
It's equal
will
to
go
Ix
to
into R.
minus infinity or plus infinity. It will be so Ix is equal to Vx by R3. So Ix is equal to Ix will tend to
Minus.
minus infinity, right?
Yes.
Contradictory. So if the contradictory things happen, that means to say that the circuit is
Negative.
in negative
Yes.
feedback. Okay. So
Yes.
if the circuit is in negative feedback, Ix will be equal to 0. If Ix is 0, Vx is also equal to 0, because Ix is equal to Vx times Vx by R3, or Vx is equal to Ix times R3. So if Ix is 0, Vx is 0. Again, the same thing you can apply. So Vi by R1, and this will be equal to minus R2 by R1 times V naught. So final thing, so over here, again, goes to infinity. So again, if a controlled source is going to infinity, if its gain is going to infinity, in that case, we will assume the controlling terminal to be greater than 0 to see if our assumption is correct or not. If it is contradictory, then it is in negative feedback. Correct? The same exercise we can follow over here. Let's assume Ix is greater than 0. So if Ix is greater than 0, A times Ix will be
Infinity.
Infinity.
infinity. So infinite current is flowing in this direction. Now this I1 will be some resistor divider between R2, R1, R3, and the current will divide. So it will be some alpha times A times Ix, right? So this will also tend to infinity, right? Is this clear?
Yeah.
Yeah, if this tends to infinity, Vx, that is equal to Vi minus I1 times R1 will tend to minus infinity. And if this happens, I3 will be equal to, Ix will be equal to, if Vx is tending to minus infinity, what will the Ix tend to?
Minus infinity.
Minus infinity.
Minus infinity, right? Our assumption is contradicted. So this circuit is also in negative feedback, and V naught will be equal to minus R2 by R1 times Vi. Is this clear?
Yeah.
Yeah. So basically, what did we learn? That any kind of controlled source, if it has infinite gain and is connected in negative feedback, can be used as an op amp. Okay. Is this statement clear to everyone?
Okay, sir.
Okay. So it's not only a voltage controlled voltage source. It can be any kind of controlled source. It only has to have a gain of infinity. If it has the gain of infinity, it can be controlled, it can be connected in negative feedback. And if it is connected in negative feedback, what will go to 0?
Controlling voltage or source.
Controlling voltage or current. So it can be controlled by either voltage or current. So whatever it is being controlled by, that parameter will go to 0. And setting that parameter to 0, you can derive rest of the currents and voltages of the circuit. The same way as you set the virtual ground voltage to 0 and then derive the current and voltages of rest of the circuit, the same thing you can do with any kind of controlled source. You can set its controlling parameter to 0 and can derive rest of the voltages and currents. Is this completely clear?
Yes, sir.
Okay. So this was a heavy concept. So after this, we will try to do some light work now. And okay, so now assume this is a voltage controlled voltage source or just an op amp with A tending to infinity. So quickly tell me what is the output gain? What is the gain from input to output?
Minus R2 divided by R1.
Minus R2 by R1, right? So basically this circuit is same as this circuit is same as this, and R3 is over here. Correct? You can see this, right? It's just that it is drawn a little differently.
R3 is in the output, sir. V naught.
Oh, sorry. It's like this, right? So if you can redraw the circuit like this, in that case, this Vx will be equal to 0 and output will be equal to minus R2 by R1. And R3 will be just a load resistance, and since output voltage of any kind of inverter, any kind of amplifier is, what is the output voltage? Sorry, output resistance. What is the output impedance of maybe any op amp connected in negative feedback? What is its output impedance? Zero, right? So if the output impedance is zero, any load that is connected at its output won't impact the output voltage of the circuit. Is this clear?
Yes, sir.
Okay. Now this happens only if the gain is infinity. If the gain is not equal to infinity, then you will see that the output voltage will be factor of something, some output, so it will be proportional to 1 upon a plus 1. You can actually find out, so this is a homework, actually find out the output voltage, output impedance if a is not equal to infinity. It will be of some factor like 1 upon a plus 1. And if in this case, if a tends to infinity, the output voltage goes to zero. You can go through this complete this thing. Is this clear?
Sir, is it the assignment problem or is anything else?
No, I mean you can just do it for a practice.
Yeah, the above one, sir. The above one which you have said now, is that an
This
assignment?
is from one of the previous assignments.
Okay, yeah.
Yeah. So
So basically, no books are giving such knowledge. What are you are giving? Even I have referred to so many books like Rai Chaitri, Gaikwad. So many books I have referred, but I haven't find this much anything like this.
so
From
that's
where you're
why
gaining this such knowledge, sir? Because we can't able to solve this one. That's what
no.
very difficult.
See, basically, that's what practice. It's only if you do a lot of practice of these kinds of concept, you will be able to understand these things. And that's why these NPTEL lectures are very important, right? Because we constantly design circuits. So see, one thing is analysis. So if the circuit is given to you, you are going to analyze it. That is one way, and you will use KCL, KVL, and all those things in order to analyze that circuit. Other thing is actually designing a circuit. That how does a circuit come up? In order, if you are able to if you are able to design a circuit, then you will be able to see these kind of things that what actually a circuit is doing. So basically,
Sir,
if
why you can
yeah,
why R3 you didn't take?
where I took the R3, right? R3 is at the output of the op amp. So I just basically redrawn this circuit.
No, in the output equation you told R3 you don't take.
That's what you just if the gain is infinite, just solve for yourself. So if the gain is infinite, your current, what will be the current that will be flowing through R1?
Sir, you have already solved this problem in the previous lecture. So the answer is minus R2 divided by R1 into A R1 divided by R1 plus R2 divided by 1 plus A R1 divided by R1 plus R2. That is the answer, I think, so, sir.
Yeah, that's what it's some complicated thing. If in that thing, if you put A as infinity, then you will get minus R2 by R1. That's
Uh,
how you do it. Okay.
it was already derived.
Yeah, understood. That's what. Why R3 has not come in this equation is because the output resistance of this particular circuit, if this circuit is only considered its output resistance, if you try to solve it, you will get as zero. Now, if the output resistance is zero, so the Thevenin looking in equivalent, let's say it's RTH. So the Thevenin equivalent can be written as this thing. So open circuit voltage will be, so let's say this, if this R3 was not there, if this R3 was not there, then you would have got minus R2 by R1. And you know that the looking in resistance from this node is 0. So you will have minus R2 by R1 times Vi, 0 resistance, and then you will have basically R3. So if this resistance is 0, no matter what R3 is, the voltage at the output will be always minus R2 by R1 times Vi. Is this clear?
Okay, sir.
Okay, so that's why R3 doesn't comes in the equation.
Yes.
Okay. So next problem. So you need to find out the transfer function of this thing, and this is written as a practical differentiator. Okay, so basically what happens is, how you can look at this kind of circuits is, so let's call this so let's say it's a non-resistive impedance. It can be capacitance, inductance, resistance, series or parallel combination of that. So let's say this is Z1. Let's say this is Z2. This is Vi. This is V0. Okay. So in this case, what will be your output voltage?
Minus Z2 divided by Z1. Z2 is a combination of R and C1 parallel, and Z1 is a combination of R1 plus 1 divided by SC.
Correct.
We solve
So
it.
basically, this is the general expression. Now, whatever network is there in place of Z1 or in place of Z2, from there you can see that, whatever. So from there you can find out the transfer function. So Z1 is the series combination of R1 and C, right? So R1 plus
Plus 1 divided by J omega C.
1 by SC.
Or 1 divided by
Okay, let's do it in terms of Laplace as of now, and later we can substitute it with j omega. So this is basically SCR1 plus 1 divided by SC. What is the other thing? What is Z2? Is the parallel combination of R and C1, right? So what is this? R times 1 by SC, R1 times 1 by SC divided by R1 plus 1 by SC. So this can be written as R1 upon SC R1 plus 1. Okay. And so what will be minus Z2 by Z1? This will be equal to SC R1 plus 1 divided by
So
SC.
Z2 is R divided by SC.
Oh, sorry. It's ulta. So it's basically R1 upon SC R1 plus 1 times.
You will solve this also. You add your add or
Yeah, so correct. You can solve it. So basically, this is what you get. Okay. So why does it says it's a practical differentiator? What will be an ideal differentiator?
without the R will be in R and C will be it's like low pass filter.
Differentiator is a low pass filter or a high pass filter?
Low pass filter.
Are
Sorry,
you sure?
integrator is low pass filter, differentiator high pass filter.
Yeah.
C and R.
So So what all components won't be there if it was an ideal differentiator?
R1, then C1.
Which R1 won't be there? So let's call this R2 and let's call this C2, or okay, whatever. So if let's say this R1 was not there, if this R1 was equal to 0 and if this C1 was equal to 0, in that case, what you will have is, and this is Vi. Okay. So basically, in this case, you will have SCR. Now, at very low frequencies, at zero frequency, will there any current flow from this node?
No, sir.
It won't, right?
Yes, sir.
So if no current is flowing from this thing, if Vi by, so if this is zero, the output voltage will be zero, and that's what you get from this. So basically, in Bode plot, it will look something like this, right? J omega axis, and if you plot the magnitude of this transfer function, you will get something like this. Now, zero at origin is your differentiator. So it's a high pass filter, right? It will block the zero frequencies, DC frequencies, and it will pass the high frequencies. Correct? So if the series resistance with this capacitance was not there, and the parallel capacitance with this resistance was not there, it would have been an ideal differentiator. But since these C1 and R1 are there, these are parasitics. So basically, what happens is, so this parallel plate capacitor will have some wire with which you will connect it to, let's say, a PCB, right? So that wire will have some series resistance, and there will be some resistance in series with this, or this resistor. For example, this resistor is made something like this. Now there will be some capacitance that will form between the soldering these ends of the capacitor. So that will act as some parallel capacitance along with the resistance. So these are some practical non-idealities that exist in the components that you have. Okay. So how will this particular transfer function look like? So what will happen is, initially it will behave as a differentiator only. But what will happen at very high frequencies, it will start going like this. So till infinite frequency, it can't behave as a differentiator. At some particular frequency, it will basically drop and become a kind of a low pass filter. So only this particular range, till the time these two poles have not hit, you will have a differentiator function. Is this clear?
Sir, why low frequency it will be high?
So at these are this resistance or this capacitances are parasitics. Okay. So wait, this will be, so this R1 times C or C times R1 will, these poles will be at very high frequencies, because this resistance is some series resistance of the wire of the capacitance, right? This R1 will be very small. If the R1 is very small, the pole that is formed between R1 times C will be at a very high frequency. Same way, this capacitance is some capacitance between the nodes of the resistance. This again will be a very small capacitance. Now, if this is a small capacitance, so C1 times R pole will be also at a very high frequency. So what will happen is, initially these poles will not hit. So 1 plus SCR1 or S, so S equal to is J omega, right? So omega is very low. So 1 plus SCR1 will be almost equal to 1. Similar way, 1 plus SC1R will also be equal to almost 1. Okay, so what you will have is only SCR1 or SCR. Sorry, it won't be SCR1. So at very low frequencies, it will behave as an integrator, differentiator. But as these two poles become active, then it will start falling, right? At very high frequencies, if omega or S is going to infinity, what will happen is SCR1 will almost be SCR1 plus 1 will almost be equal to SCR1, and similarly SC1R plus 1 will almost be equal to SC1R. So you will have SCR divided by SC1R times SCR1. So this will be approximately equal. So this S will be cut, this R and C will be cut. So you will have SC1R1. So this will basically at high frequency fall with increasing frequency. Is this clear?
Yes.
Yeah. So a practical differentiator doesn't behave as a differentiator till infinite frequency. After certain frequency, due to parasitics, it will just drop down. So I hope that is clear. Now this is just a one word kind of question. So special case of non-inverting amplifier in which all the output voltage is fed back to the inverting input is called. So what it is trying to say, how does a non-inverting amplifier looks? So there will be some input. Let's say this is RF, this is R1, and this is ground. This is how an non-inverting amplifier looks like, right?
Yeah.
Yeah. So if this is an non-inverting amplifier, what is the gain at the output?
1 plus RF by R1 into
1 plus RF by R1 times Vi, correct?
yeah.
Okay. Now what does it says? All the output voltage is fed back to the inverting input. What does this mean? So how much of the output voltage is being fed back to the inverting input in this case? So if output voltage is V naught, what is Vi or V minus?
V naught.
No, it's not V naught, right? If output voltage is equal to V naught, what is Vm? It is resistor divider between RF and R1, right? Can you see this? Okay, so it's basically equal to R1 upon RF plus R1 times V naught.
Yeah.
Correct? So a fraction of the output voltage is being fed back to the inverting terminal, right? Let's call this fraction beta. And if there is virtual ground, this Vm will be equal to Vi, right?
Yeah.
So if a fraction of the input voltage, so this will be less than 1, right? You can see this. So R1 by RF plus R1, a voltage divider will be less than 1, right? Okay, so if then Vm is equal to Vi, so Vi by beta is equal to V naught, correct? And what is this beta? This beta is RF plus R1 by R1 times Vi. This is equal to 1 plus Rf by R1. Okay. So basically, in English, what you can say is, if let's say a fraction of the output voltage is fed back to the input, then the gain from the input to output will be reciprocal of that fraction. Did my statement make sense to you guys? If a
Can you,
fraction,
can you explain
sorry,
with respect to the answer, sir?
okay, we will get to that. We will just get to that. Basically, if a fraction beta of, so this is basically equal to beta times V naught. So if a fraction beta of the output voltage is fed back to the input, to the inverting input, the gain from the positive terminal to the output will be reciprocal of that fraction. That is 1 by beta.
Yeah, sir. Got it.
Okay. So if instead of this fraction, if let's say all of my output voltage was fed back to the input, how will that circuit look like? If beta is equal to 1, if beta is equal to 1, what will happen to R1 or RF? How can beta become equal to 1 in this equation? So
RF must be very small compared to R1.
RF must be, or you can say that RF is equal to 0, R1 is equal to infinity. Correct?
Yes, sir.
In that case, what is happening? All of the output voltage is being fed to the inverting terminal of the op amp. So it will basically look like this. So if R1 is infinity, this is open circuit. So nothing will be there between that, and RF is equal to 0. This is a short circuit. So what is this?
Voltage follow.
Okay. So if all of the output is being fed back to the input, that means to say so this beta is called, there is a name to this beta. This beta is called feedback factor. Correct. So if so in English, if it is written all of the output is fed back to the voltage, that means to say this guy is trying to say that feedback factor is equal to 1. Okay. So if feedback factor is equal to 1, your RF will be equal to 0 and R1 will be equal to infinity. So this will behave as a voltage follower. And this you always keep in mind, whatever the feedback factor is, the gain is proportional to a reciprocal of the feedback factor. Is this clear?
Yes, sir.
Okay. So this figure represents what?
Integrate.
Integrator. Okay, and now can you guys help me see how it is an integrator? So let's not try to solve it with Laplace. Let's actually try to solve it with, so you know the time domain expression for current and voltage for capacitance, right?
V naught by VA is equal to 1 minus 1 divided by SCR.
Okay, that's what. So this is basically in Laplace domain, right? Let's assume we don't know Laplace. Let's see what happens in time domain. So you know that there is a Laplace domain, and please answer for last question. Last question as in this one, right? So this is basically a voltage follower. Okay. So over here, let's try to solve this question in time domain. If let's say this we call as VC, and let's call this as IC. Okay. So what is IC equal to?
C into dVc divided by dt.
C into dVc divided by dt, correct? Okay. Now, so this current is equal to 0, right? And this current is equal to
IC, sir.
IC. And what is this equal to? So if this is, let's say, R. So IC is equal to VI by R, right? Okay. So basically IC, and what is output voltage? V naught.
Minus
V
IC divided by into 1 divided by SC, sir. One,
No, forget about SC. And I am not interested in Laplace domain. I will solve this. I am trying to solve this in time domain. See how it is an integrator. So basically, V naught is equal to minus of Vc, right? If this voltage is 0 and the voltage across capacitance is Vc, so V naught is equal to minus of Vc, correct?
Yes, sir. Yeah.
Okay. So what you can write over here, IC as minus C dV naught by dt, correct? So what we have, Vi by R is equal to C dV naught by dt. That can be written as minus 1 by C. So dV naught is equal to minus 1 by RC times Vi dt, correct? Now if we integrate both sides from let's say 0 to V naught, and this is 0 to time t. Okay, so basically what we will have, integration of unity is equal to
V naught is equal to minus 1 divided by RC
minus,
integration of 0 to t Vi into d.
okay. So Vi can be a function, so you cannot just write t, right? If Vi was, let's say, a constant, in that case, this integral will be equal to t. But Vi can be a function of some time, right? So if Vi is a function of time, then whatever this function is, the integral will be the integration of that particular function. Okay, so this is how it behaves as an integrator in time domain. And this integration only is basically 1 by s. If you do the Laplace transform, integration in time domain means 1 by s in frequency domain. So from there you get 1 by SCR. So that is a Laplace domain concept. You can, in a signals and system, you might have studied this. Is this clear?
Yes, sir.
Yes, sir.
Okay. So the same thing you can do with the differentiator as well. Can you guys help me do it with the differentiator? This is a differentiator, right? This is output voltage.
V naught is equal to RC into dVi divided by dt it comes.
Yeah, correct. RC into dVi by dt. So if you try to solve it in the same way as we solved for the time domain expression for the integrator, you will end up with this expression. So this is basically what it is doing. It whatever function of time your Vi is, it basically differentiated to give you the output voltage. Is this clear? Okay. Next question. So, a circuit of a non-inverting summing op-amp has, so basically it has V1 equal to plus 2 volt, V2 equal to minus 4 volt, V3 equal to plus 5 volt. Okay, so basically three things are being summed. Can you help me write the circuit of a summing op-amp? And it's non-inverting, right? So input will be on which terminal, plus or minus?
Plus.
Plus. Okay. So, and the feedback which will be on which terminal?
Minus.
Minus. So let's say there is some feedback over here. Let's call this RF. Okay. And so how will you give the input? You will have multiple inputs, right? So this is a non-inverting summing amplifier. So V1, V2, V3 will be summed at be present at the output. Correct? So what does it says? V1 is equal to 2 volts, V4 is equal to minus 4 volts, and V3 is equal to 5 volts. And input resistors of all three are same and equal to 1 kilo ohm. So this is 1K, 1K, 1K. Okay. The feedback resistor is 2 kilo ohms. Then it is asked that what is the determine the voltage Vp at the non-inverting pin and the output voltage. So let's say, so this is basically called Vp and this is your output voltage. So what will be your Vm? Vm will be equal to,
Is
guys,
it 0?
sorry,
0?
why it will be what is virtual ground? The
VP?
input, yeah, the input to the op amp basically differentially has to be zero, right? So if this is Vp, Vp and Vm will be equal to zero. In this case, so virtual ground concept is there in non-inverting amplifier where positive terminal is connected to ground, so negative will also connect to ground. In case of an inverting amplifier, in non-inverting amplifier, positive terminal has some voltage. It is called virtual short. So there is virtual short between Vp and Vm. Virtual short is a more general term. So whatever happens to Vp will happen to Vm as well. Okay. If Vp is connected to ground, then it will be virtual ground. If Vp is connected to some other voltage, it will be virtually short to Vm. So Vm will be equal to Vp. And what is V naught equal to? Guys, what is V naught equal to? Will there any current flow in this direction? What is the current?
V naught minus VP by RF.
V naught minus Vp by
RF.
RF. Correct. Where will this current flow? Is there any path for this current to flow? Guys, can this current flow in the negative terminal of the op amp? No, right? The input to the op amp is infinite impedance, correct?
Yes,
Is there? Yeah. So if the input to the so no current can flow in this direction, so I should be equal to 0, right?
ideal case.
Yeah. So this is an ideal op amp only. So I should be equal to 0, and V naught is equal to Vm. If no current is flowing through this resistor, there will be no voltage drop across this resistor. Correct. So if V naught is equal to so basically what we have is Vm is equal to Vp is equal to V naught. Okay. Now what is Vp? How can you find out Vp? So looking at this, looking at the options, can you quickly tell me what will be the answer? Don't solve it. Just quickly tell me the answer by just looking at the options. Option D. Why?
V naught equals to VP.
V naught equal to Vp, and that is there in only one option, so it has to be option D. How can you find out Vp? It will be 2 minus 4 by 5, correct? So that's how you will find out Vp. Is this clear? Actually, it will be 0.5 by 1.5. So actually, it will be. So there is something missing in this question. The input resistors of all three input signals are the same and equal to 1 kilo ohm. Feedback resistor is 2 kilo ohm. So one thing that is missing is just a minute. So it shouldn't be this thing. So basically, it should be. How will you find out VP? So you will have 1 kilo ohm. You can use superposition, right? This is a linear circuit. This particular circuit is a linear circuit, so you can use superposition. So we have 1 kilo ohm, then 1 kilo ohm over here, and 1 kilo ohm over here. So you will just make V2 and V3 equal to 0. So due to this, Vp due to V1 will be equal to V1 by, so V1 into 1 kilo ohm by 3 kilo ohms. Sorry, V1 into 0.5 kilo ohms. So why 0.5? This 1 and 1 will in parallel will be 0.5 kilo ohms. So it will be basically divided by 1.5 kilo ohms. This is V1 by 3. Same thing can be done for V2 and V3. So basically Vp will be equal to V1 plus V2 plus V3 by 3. Okay. So if V1 plus V2 by V3 by 3 you have, so actually it will be 2 minus 4 plus 5 by 3, and this is equal to 1 volt. So actually the option should have been 1 volt and 1 volt, but yeah, this is different. When it could, so if there was some 1 kilo ohm resistor over here also, in that case, what would happen? In that case, V naught would have been equal to Vp times 1 plus Rf by R1. And if this resistor was 1 kilo ohm, in that case, Vp times 3 it will come. This is 2 kilo ohms, right? So V naught would have been equal to 3 volts. So then this option would have been correct. Okay.
Yes, sir.
Okay. So any doubt so far? Do you want? So these were the questions that I had for today. Do you have any other doubts or any other things that you want to discuss?
Sir, the assignment questions and all, it's very, very tough.
Okay, so you will just try to solve them and see if you can. So, if you have any problems or any question that you want to solve from assignments, you can always mention it to me. And in next session or maybe this session, actually, I don't have the assignment right now, so I will have to dig it up. So, if you want some question that can be discussed in the next session. And of course, in this session, I cannot, so the deadline has not come for the assignment, right? So I cannot discuss the assignment right now. But in the next session, when the assignment is submitted, then you can ask for some particular question and we can solve that in this tutorial as well.
Sure. Thank you.
Okay, so any other doubts?
No doubts in this section. Excellent section.
Okay, so if there are no other doubts, so this was it for today's tutorial session. Thank you guys for attending.
Okay, sir.
Yeah.
Sir, can you spell the beta one more time?